Back again. So this is basically episode number 8, and this is going to be part number 4 of data types in MPI. We were talking about packing and unpacking. We're going to continue by this sentence. Derived data types, which are described in section 5.1, allow one in most cases to avoid explicit packing and unpacking. So you know that packing and unpacking probably is not that efficient because you're gonna have some memory to memory copying. So this is not gonna be as efficient. But this is one way. If you have non-contiguous data, then you can basically pack them inside contiguous data buffers and then send them through the network. And then on the receiving side, you unpack them and then try to basically use them. And then the user specifies the layout of the data to be sent or received, and the communication library directly accesses a non-contiguous buffer. This is in the case that if you try to use that general data type that we saw in section 5.1 with different data type constructors. The pack-unpack routines are provided for compatibility with previous libraries. Very important. And now we move in MPI pack. Let's see the list of arguments. It needs an in buffer, in count data type. Then it needs out buffer, but instead of a count and data type, it has out size and position. What is out size? Out size is the output buffer size. It works with bytes, not with counts or not with integers. It works with bytes. And then position is going to be the current position in buffer. Again, this one also works with bytes. So that's packing. When you want to unpack stuff, these arguments sort of reverse. So first you're going to have in buffer, then the size, and then the position. Exactly these two things are again working with bytes. And then you populate it with out buffer, out count, and the data type. And then finally you have the communicator. So we have an example for this one. I think it was called pack unpack.c. So pack unpack.c. Right here we have a count of 10 elements of the same example that we're using over and over, this data, a double followed by a character. So we know that the extent of this one is 16. So 10 counts of them is 10 times 16 is going to be 160 bytes. But let's say we use roughly 200 bytes. So our buffer is going to be 200 bytes because it has type of char. So rank number 0 is going to basically populate my data, which is 10 sort of counts of that data struct. It's going to try to uniquely populate them. And then we start packing here. For packing, again, you pass in all the argument lists that you need. What is important here is that this 200 is not an exact size of the data basically that you want to pack, but it is basically the maximum size that you pass in here, or it is an estimate. And then first you pack your doubles. That's why we have this .d here. And then second, you pack your characters. That's why we have this .c here. The count is always going to be 1. And this type is double for the first part, and it's going to be char for the second part. And the rest is basically easy to understand. We print basically the original data that we have on process 0, and then on the receiving side, we send it. And then on the receiving side, one thing which is super important is that the type that we use here is MPI packed. So that is super important. And on the receiving side, again, we are getting MPI packed from process 0 with this tag 42 and this communicator, and we ignore the status here. Then we try to unpack stuff. Again, we use 200 here. This is not the exact size that we basically receive, but this is the maximum size that we basically need. So this is the unpacked version of it. And then we populate the unpacked version first with the doubles because we have packed the doubles first, and then we unpack the characters. And then we try to print basically the received data and then try to compare the original data with the received data. So let's go with MPI CC pack unpack. Whoops. .c and MPI run. Okay, you see that we start with 0 and character A, and we end up with 28 and J. So that's the original data. Whoops. But on the receiving end, we have 0 and A in the beginning, and finally we have 28 and J. So message has been transferred correctly. And then we go down here. We have MPI pack size. We have a different example for this one. You remember that we used 200 bytes. We said it's just a rough estimate of what it's going to be, basically the size. But then you can use MPI pack size to know exactly how much you need as your size. So this is the, which example is that? See pack size .c. So here we try to basically use MPI pack size with the count, that's 10 elements, and then we have doubles. This is the communicator, and this is going to be our double size. It's just going to hold, it's an integer to hold the size of all these 10 counts of doubles and the size of all the counts of sort of characters. And then the pack size is going to be sort of addition of those two sizes. And then we're going to have our buffer exactly with the size of pack size. And then everything else is the same. So you populate it, you pack it again, but this time instead of 200, you use pack size. You print the original data, and then on the receiving side, again, you try to unpack it and print the received data. So MPI CC, everything is the same. With pack size.c and MPI run. So again, you start with 0 and A, finalize it with 28 and J, again 0 and A, 28 and J. So here also it shows that the message has been transferred correctly. There are some examples here that we don't care about them because we already have our own examples. Okay, this is the final topic that we want to talk about. This is the canonical MPI pack and MPI unpack. So this is basically 4 procedures which are suitable for portability when you are working with really, really heterogeneous sort of systems. Usually in clusters, the computing nodes, you know, they have the same sort of architecture and the same system and everything. But if you are really working with a distributed system that is heterogeneous, that they have different systems and stuff like that, so then this canonical packing and unpacking is the way to go for you. These procedures read and write data to or from the buffer in the external 32 data format, which is a data representation format specified in section 14.5.2. Calculate the size needed for packing. The first argument specifies the data format for future extensibility, but currently the only valid value is this for data representation is the external 32 right now. The buffer will contain exactly the packed data without headers. MPI byte should be used to send and receive data that is packed using MPI packed external. So this is another difference, that we were using MPI packed for send and receive. Now we need to use MPI byte with MPI packed external. So this is how it looks. As I said, one extra argument here, which gets the data representation. Right now, it only works with external 32, but this is done for a future extensibility. So we have pack unpack external here. Let's take a look at this example. Pack unpack external. This is essentially the same example, 10 counts of that struct, but this time we're going to have, again, the rough estimate of 200 bytes. Also note that the position is not going to be an integer. The position in this time is going to be MPI aint once you're working with external packing, MPI pack external. And then you populate it. Everything is the same. You pack it with MPI pack external, and then you pass in this external 32. And then the rest of this stuff, you can read the argument list in the standard. And then first you pack your doubles, then you pack your characters with this external representation. You know that it is portable. Then you print your original data. you send your data over, but this time you notice that you're using MPI byte, not MPI packed. And on the receiving side, again, you are using MPI byte. Also, I forgot to mention that with MPI packed and probably also MPI byte, the restrictions of type matching are basically relaxed. So here it can be matched with sort of anything. And then on the receiving side, you unpack stuff, again, with external 32 representation. And first the doubles, and then the characters, and then you print the receiving side data. So MPI CC, pack, unpack external, and MPI run. Whoops. So this is again the same pattern that you see with external 32 representation. And then we have the same example because we have also a size component, which is called as MPI pack external size, similar to MPI pack size. So let's go to, what was the name? Pack size external, pack size external. Exactly the same sort of a story here, 10 counts of that data, but this time we're going to have different position, different type for position, MPI A int, and also the sizes for a double and character. These are also not ints anymore, they are MPI A int. Then you use MPI pack external size, you pass in the necessary arguments, and then you add up those two, the sizes needed for doubles, the sizes needed for characters, and then you patch up your buffer with the exact size of pack size. The rest is the same basically. You just pack your data, you populate it, you pack your data with the external 32 representation, you print the original data, and on the receiving side, again, you send it with MPI byte, and then on the receiving side, you unpack everything and you basically print the received data. So MPI CC, let's see the last and final example. Hopefully we're going to be done. Okay, so here it also shows that the message is transferred correctly with 0 and A and 28 and J. There we go. That was the last thing, I think. Yeah, we reached chapter number 6, which is collective communication. Okay, so it took me I don't know how many hours, but I started so late at night, and now it's basically the next morning. It's 5:30 in the morning. But I do hope that you learned something from this video. This was data types in MPI, a very important chapter. I hope you learned something from this video and hope to see you in the next one.